Good day, ladies and gentlemen. Let's talk about combining functions. This is also referred to as operations on functions. And if you think about the operations on real numbers, they are very familiar to you. They are adding, subtracting, multiplying, and dividing, right? Well, we're going to do exactly the same thing with functions. Let's imagine two functions. Now we can talk about these functions in terms of combining them through the operations of adding, subtracting, multiplying, and dividing. Let's first of all look at the sum function. And it is written f plus g of x. And it means literally whatever f of x is plus whatever g of x is. Hey, that's no surprise, huh? So f plus g of x, the sum function, simply means whatever f of x is, 2x plus 3, added to whatever g of x is, x minus 1. Combine like terms, it's 3x plus 2. So I get a whole new function when I do this sum function or the addition function. Start with two functions, I end up with a third new function. Now, as soon as I have f plus g of x defined as 3x plus 2, or even if I don't, I can talk about f plus g of, let's say, something. 2. All this means is f of 2, the first function evaluated at 2, plus the second function evaluated at 2. F of 2 means 2 times 2 plus 3 plus, oops, I shouldn't have put that there. 2 times 2 plus 3 plus g of x means 2 minus 1. So 2 times 2 is 4 plus 3. 2 minus 1 is 1 plus 1. That gives me 8. If I started with the combined function itself, f plus g of x is 3x plus 2. Then f plus g of 2, I could talk about as simply 3 times 2 plus 2. What do you know? Same thing, 8. So here's the definition of the sum function. Simply means add your two functions together. No big challenge, right? Well, let's try the difference function. And you're probably already ahead of me here. It looks like f minus g of x. And no surprise, f minus g of x means whatever f of x is minus whatever g of x is. Now here's where I have to be really careful. F of x is 2x plus 3 minus g of x is x minus 1. I'm going to let that sit there just for a second and let you look at it and think, did I do that correctly? In fact, I did not, because this says subtract whatever g of x is. That's g of x. The way I subtract whatever g of x is putting it in parentheses. I have to apply the subtraction or the negative sign to everything in g of x. So that means 2x plus 3 minus x plus 1. 2x minus x, 3 plus 1, 4. So there's my new function, f minus g of x. But here's the definition of the difference function. If I wanted to do f minus g of, let's say, 7, well, there's f minus g right there. It's just going to be 7 plus 4, or 11. So I have a sum function, a difference function. No big surprise so far. All right, how about the product function? And it's defined as fg of x is, what do you think? Whatever f of x is times whatever g of x is. It's just the multiplication of the two individual functions. No big deal, no surprise. So this is my definition of the product function. Let's apply this to our two functions, 2x plus 3, and g of x is x minus 1. So fg of x means f of x times g of x. That means 2x plus 3 times x minus 1. Hey, I got two things times two things. That means FOIL, 2x squared minus 2x plus 3x minus 3. Middle two terms are like terms. Combine them. 2x squared plus x minus 3. So here's my new function, the product function, when I have these two individual functions, f of x and g of x. And once I have this, I can talk about f g of, let's say, 5. The product function of these two functions, evaluated at 5, is going to be putting a 5 everywhere there's an x. Do my exponents first. So it's 50 plus 5 is 55, minus 3 is 52. So I can evaluate my product function at a particular numeric value. All right, let's look at the final possibility, the quotient function. Now, of course, this is going to change when f of x and g of x change. And on your Hawks problems, you will not have this f of x and this g of x, but you'll be doing the same thing. So the look of it is f over g of x, and no surprise at all, that's simply defined as f of x over g of x. So in this case, it's defined to be 2x plus 3 over x minus 1. All right, let's evaluate the quotient function for a particular numeric option, like f over g of 10. That means everywhere there's an x, I'm going to put a 10. That's 20 minus 3, that's 17. 10 minus 1 is 9. 17 ninths. So I can get a general evaluation of the function, or I can evaluate it at a specific numeric value, substituting that number everywhere there's an x. Now here's my definition of the quotient function. Now one thing Hawks is going to ask you to do on occasion is find the domain of these particular functions. Now, as soon as I say the word, or Hawk says the word domain, you should be thinking of this particular worksheet. I have given you this on 2 occasions. I will give it to you again with these notes on this occasion. The domain is limited only in 2 instances, and that is when you have a fraction where the denominator could be 0, or where you have a radical with an even index like a square root, where you could get a negative under this radical. So we'll keep this in mind as we talk about the domain of these particular functions. So let's look at this new function right here. The sum function is 3x plus 2. What's its domain? Now, as soon as I say domain, you should ask yourself the 2 questions at the bottom of your page. First of all, will any value of x result in a 0 denominator? Hey, there's not a denominator, so I can't have a 0 denominator, so I get a no. Second question, will any value of x result in a negative under a radical with an even index, like a square root? Well, of course, there's no radical. So I get 2 no's to my 2 questions, and if you answer no to both questions, your domain is all real numbers. So my domain here, all real numbers. And the way we write that in interval fashion is from negative infinity to infinity. All right, let's look at this guy, the difference function. Domain. Hey, any value of x result in a 0 denominator? Nope, no fraction. Any value of x result in a negative under a radical? Nope, no radical. So I get 2 no answers, all real numbers. That was easy. Let's look at this guy. Domain. Hey, any value of x result in a 0 denominator? No fraction. Any value of x result in a negative under a radical? No radical. I get 2 no answers. Domain, all real numbers. So as long as I have no fraction and no radical, my domain is going to be all real numbers. All right, here is my quotient function. Question number 1. I'm asked about the domain. Will any value of x result in a 0 denominator? I'm thinking maybe so. You see, I got a denominator here, and there's an x in the denominator. Very real possibility that something could result in a 0 denominator. Some of you can see what would make the denominator 0. Others of you are going to have to use the strategy. Set the denominator equal to 0 and solve. Here's my denominator. Set it equal to 0 and solve. Add 1 to both sides. X equal 1. Now that's not my domain. When you solve the equation, you've just discovered what x cannot be. Your domain is everything except 1. So my domain, all real numbers except 1. Now, how am I going to write that in interval fashion? Remember, the number line basically looks like this. 1 is the one thing that's not in my solution set. So I got all this is good, and all this is good. I just have one value that's not in my solution set. How do I write that? With interval notation. I say it like this: from negative infinity to 1. Oh, but don't include 1 because it's not included. Together with 1 all the way to infinity. But don't include 1 because it's the one value that's not included in your domain. So here's a picture of the domain saying all real numbers except 1. If it was all real numbers except 17, you go negative infinity 17 parentheses, union parentheses 17 to infinity. So whatever number you're trying to exclude goes in this position right here. All right, so those are my 4 familiar operations: adding, subtracting, multiplying, and dividing. But surprise, surprise, there is a 5th operation that only applies to functions. It does not apply to real numbers. It's called the composition of functions. Now I have symbols. I have symbols for addition, subtraction, multiplication, and division. I do not yet have a symbol for composition, so we need to come up with one. Let's use our same 2 functions. And I can use any number of functions. I'm just choosing some simple ones. Here are my 2 functions. The way I say the composition of functions looks like this. F, little bitty circle, G of x. See, it's not plus, it's not minus, it's not times, it's not division, it's something else. And here's what it means. F of g of x, this is the composition of functions. F of g of x may be written as f, the first function, evaluated at g of x, the second function. Here is my definition of composition of functions. It's the first function evaluated at the second function. Now that may not be clear. Let me give you a couple of examples that maybe make this a little bit more obvious. Let's look at the function f, and let's find out what f of 2 is. Well, that means everywhere there's an x, I put a 2, right? 4 plus 3 is 7. Let's do f of negative 5. Well, everywhere there's an x, I put a negative 5. Right? And evaluate. Negative 10 plus 3 is negative 7. Let's do f of 100. That means everywhere there's an x, I put 100. It's 200 plus 3, 203. So when I evaluate f at a particular numeric choice, I simply substitute that value everywhere there's an x. Well, in the composition of functions, we're not going to evaluate f at a number. We're going to evaluate f at a new function, in this case, g of x. So f of g of x means exactly what it did here. It means 2 times something plus 3, right? 2 times something plus 3. But the something that I substitute for the x is not a number, it's a whole new function, g of x. G of x is x minus 1. So instead of putting 100 here, or negative 5 here, or 2 here, I put the entire function g of x wherever there was an x in my first function. Now this isn't finished, of course. I need to do a little distributive and a little bit of simplification. These are like terms. So here's the composition of these 2 functions. F of g of x turns out to be a new function, 2x plus 1. Doesn't look like either one of my originals. All right, let's look at 2 different functions. Let's say f of x is the square root of x, and g of x is 3x plus 2. And we want to talk about what is f of g. Let me write it the first way. F of g of x. Could write it this way, could write it that way. It says the same thing. All right, let me show you a little shortcut here to find the composition of functions. I've got a first function and a second function, right? Take your first function and write it, except leave the x out. In the place of the x, just leave a blank. Now, in that blank, I put the second function at 3x plus 2. So there is my composition of functions, f of g of x. Hey, would it matter if I change the order of my functions? Let's see. Let's see what g of f of x would be. Well, I start with my first function, 3x plus 2, and everywhere there's an x, I leave a blank. You can go ahead and put a blank. And then in that blank, I put my second function, f of x, which is square root of x. So my composition of functions here, 3 square root of x plus 2. Did I get the same thing? I did not. These are different. So we can say that the composition of functions is not commutative. It matters in which order I do the composition. It matters which function is listed first. Hey, it doesn't matter in which order I multiply things, it doesn't matter in which order I add things, but it does matter in which order I do the composition of functions. All right, let's look at some of your Hawk's problems, and hopefully see that they're not too difficult. All right, this says consider the following. F, hey, do we know what f is? We don't. All we know is that f of negative 3 is 13. Do you know what g is? Nope, you don't. All you know is that g of negative 3 is negative 10. This says find f plus g of negative 3. Now, I know by definition that that means f of negative 3 plus g of negative 3. That's the definition of the sum function. So f of negative 3 is 13. G of negative 3 is negative 10. 13 plus negative 10 is 3. Got it. Well, that's not hard at all. Do this one. F minus g of negative 3. That means f of negative 3 minus g of negative 3. F of negative 3 is 13 minus g of negative 3, which is negative 10. Don't forget that's a minus a negative 10. That's 23. This isn't bad. F times g of negative 3, all that means is f of negative 3 times g of negative 3. That means 13 times negative 10. It means negative 130. And finally, f over g of negative 3, all that means is f of negative 3 over g of negative 3. That's 13 over negative 10. I'm assuming Hawks would take it like that. Negative 13/10. Hey, that's not bad at all. No problem there at all. Just using our definition of the sum, difference, product, and quotient functions. Pretty much the same thing here, except instead of saying f of 4 is 5 and f of 2 is negative 5, I give you some ordered pairs. Remember, this is another way I can show what a function is, a list of ordered pairs. G, this list of ordered pairs. So let's do the same thing. F plus g of 2, by definition, that means f of 2 plus g of 2. Can I find f of 2? It's whatever 2 is associated with. F of 2 is negative 5. Can I find g of 2? Who's g? 2 is related to 1. So I get negative 4 for f plus g of 2. Let's do f minus g of 2. All that means is f of 2 minus g of 2. I already know what f of 2 is. It's negative 5 minus g of 2, which is 1. Negative 5 minus 1, negative 6. F times g of 2, or fg of 2, means f of 2 times g of 2. Just the product of the two evaluated, the two functions evaluated at 2. I already know what f of 2 is. It's negative 5. I know what g of 2 is. It's 1, negative 5. And finally, f over g of 2 simply means f of 2 over g of 2. F of 2 is negative 5. G of 2 is 1, negative 5. Not too bad, except instead of telling me what f of something is, it gives me an ordered pair to let me know what that function is at a particular value. All right, here's a composition. Find f of g of 1 for the following functions. So f of g of 1 by definition means f of g of 1. That's the definition of composition of functions right there. F of g of x means f of g of x. F of g of 1 means f of g of 1. This is typical order of operations. Work inside your parentheses first. What's g of 1? They tell me. G of 1 is negative 5. So this means f of negative 5. Do I know what f of negative 5 is? What do you know? F of negative 5 is negative 2. So here's the important concept, the definition. F of g of 1 is the first function evaluated at g of 1. Told what that is? I'm told what that is. They give me enough information to figure out what f of g of 1 is. All right, a little bit more sophisticated functions, but I can still handle this. Find f plus g of negative 2. That's f of negative 2 plus g of negative 2. Now, f of negative 2 means everywhere there's an x, I put a negative 2. Plus, g of negative 2 says everywhere there's an x, I put a negative 2. Now you might want to use your calculator for this. If you're gonna misthink it, a negative number cubed is going to be a negative number. Negative 2 cubed is negative 8 plus 2 minus 2 minus 1. Those guys cancel. Negative 8 minus 1, negative 9. Let's try this one. F minus g of negative 2. By definition, f of negative 2 minus g of negative 2. F of negative 2, already done that. well, I haven't actually already done that. I did it in parts, so I better do it again. F of negative 2 is negative 2 cubed plus 2, which by the way is negative 8 plus 2, negative 6. That's f of negative 2 minus g of negative 2. Says everywhere there's an x, I put a negative 2. But it's the whole thing. Negative 2 minus 1. Put g of x in parentheses because I'm subtracting the entirety of g of negative 2. Whatever g of negative 2 is, here it is, subtract the whole thing. That's negative 3, right? So this is minus negative 3. It's negative 6 plus 3, negative 3. All right, once again, f times g of negative 2. That means evaluate f at negative 2, multiply that by g evaluated at negative 2. Now I've already evaluated f of negative 2. It's negative 6. And I have evaluated g of negative 2. It's negative 3. So the product of these two is positive 18. And finally, f of negative 2 over g of negative 2. F of negative 2 is negative 6. G of negative 2 is negative 3. That gives me a positive 2. Not a big deal, just a little bit more sophisticated function here to evaluate. All right. This is going to be some backwards thinking, so to speak. What we're talking about here is undoing the composition of functions. Undoing the composition of functions. The composition of functions takes two functions and mixes them together to form a new function. What this exercise is asking me to do is to come up with two functions that have been blended to get this thing right here. So here's my new blended function, my composed function. It says find g of x and h of x. Find two functions such that g of h of x equals this new guy. So I have already done somewhere in the past a composition of functions, and this is my result. What two functions were composed in order to give me this new composition of functions? This is a challenging problem. You won't have one like this on your test. You will have one like this on your Hawks. So let's look at it like this. Take your new function and describe it in general terms. Think of it in general terms. This new function is, are you ready? It's a square root of something plus a number. It's a square root of something plus a number, right? That's the general way I could describe this function right here. It's the square root of something plus a number. In fact, plus the number 2. So when I think about one of the functions, it could be this guy right here. The square root of something plus a number. That is exactly this. The square root of something plus a number. So my first function, the one on the outside, is the way I'm going to describe my general expression of this guy right here. So g of x is this. My g of x is the square root of something plus a number. Well, what have I put in the place of the something in my composed function. It's this right here. So the something is going to be my internal function, h of x, and that's going to be 3x cubed plus 4. So let's look at these two functions. G of x equals the square root of x plus 2. H of x equals 3x cubed plus 4. This is my answer, by the way, for Hawks. That's what they want. Let's see if the composition of these two functions gives me that. All right, let's do g of h of x. G of h of x, which could also be written as g of h of x, right? And here's the little hint I gave you about how to flesh this out. Take your first function, the first function mentioned, and write it out, except everywhere there's an x, you put a blank. So g of x is square root of x plus 2. So I'm just going to write square root of blank plus 2. Then in that blank, you put the second function. What is the second function? 3x cubed plus 4. Hey, what do you know? I got the original function. When I composed these two functions in this order, if they'd been reversed, I wouldn't have gotten the right answer. When I compose these two functions in this order, I get my original composed function. This is not easy. It's kind of a backwards thinking. This is my final result. What two functions did I use? So your strategy is going to be describe this thing in general. That's going to be your first function. And then how specific do you want to apply it in order to get to your composed function? Again, difficult. Something like this will not be on your final test. All right, wow, two sophisticated functions here. It says find f of g of 1 for the following two functions. So let's f of g of 1 is defined to be f of g of 1. That's the definition of composition of functions. So the first thing I want to do is find g of 1. That's my inside the parentheses evaluation. So I want to take g and evaluate it at 1. So everywhere there's an x, I'm going to put a 1. 1 squared is just 1. X squared is 16. Hey, that's 4. So f of g of 1 turns out to be f of 4. How do I know? I figured out what g of 1 is. G of 1 is 4. Now I'm going to evaluate f at 4. That means everywhere there is a x, I'm going to put a 4. So it's the square root of 5 times 4. I'll go ahead and write that out so you know where it's coming from. Over 6. That's the square root of 20 over 6. Now round to 2 decimal places if necessary. So what I'm going to do is find out what 20 over 6 is in decimal form. 20 divided 6 is, and I get 3.33333, repeating. Then I need to take the square root of that. Take the square root of it, and I get 1.8257, etc. It says round to 2 decimal places. I don't know if you're aware of this, but if I'm rounding to 2 decimal places, I look at the 3rd decimal place to see if I round this up or leave it alone. And you know the drill. If it's 5 or greater, and it is, I round the next digit up 1. So this becomes 1.83. So this is approximately equal to, that's what that little squiggly means, approximately equal to 1.83. That's what you will put into your Hawk's blank when it asks you to round to 2 decimal places. Is that okay? So f of g of 1 is defined to be the first function evaluated at g of 1. I find out what g of 1 is. It turns out to be 4. That means this thing right here is 4. So I find out what f of 4 is. Everywhere there's an x, I put a 4. Turns out to be 20 over 6. Square root of that turns out to be this right here. Pretty good problem. All right. Consider the following functions. Hey, these are pretty sophisticated problems right here. Find the formula for f plus g of x. So let's do that first. F plus g of x simply means, by definition, go back to your definitions, f of x plus g of x. So it means this plus that. No like terms here, so this is basically my answer right here. Find the formula for f plus g of x. Got it. Then find the domain for f plus g of x. I need to find the domain for this guy right here in the box. As soon as I'm asked to think about the domain, I get my worksheet and I ask myself this question. Will any value of x result in a 0 denominator? Hey, there's no fractions, so there's no denominators. So I get a no to my first question. Second question. Will any value of x result in a negative under a radical with an even index? Hey, I got a radical with the even index as a square root. And yeah, I can pick some numbers that are going to make negatives, like if I pick 0, 0 minus 4, negative 4. Problem. If I pick 1, 1 minus 4, negative 3, square root of that, problem. So I can pick all sorts of numbers, negative 200 minus 4, negative 204. All sorts of numbers that give me negative under this radical. So my domain is going to be limited. What's it going to be? Don't try to think it out, work it out. If you get a yes to this question, follow strategy number 2. So I go to the strategy that deals with the radicals. Take the radicand, that's what's under the radical, x minus 4. And my strategy tells me to set it greater than or equal to 0 and solve this guy. Add 4 to both sides, no big deal. X is greater than or equal to 4. And once I solve the inequality, that is your domain. Hey, follow your strategies. They're helpful. Solve the inequality. There it is. That's my domain. So my domain is anything greater than or equal to 4. If I showed you on the number line what that looked like, here's 4. It's anything greater than or equal to 4. The equal to means I got a bracket here and not a parentheses. 4 is included. So there's the picture. They're going to ask me to express it in interval fashion. So it's going to be, it's going to be from 4, bracket, because I got a bracket here, all the way to infinity. There's my interval expression for my domain. All right, let's try this guy. Find the formula for f over g of x. F over g of x simply means f of x over g of x. So that means f of x, I'll go ahead and write it out, f of x over g of x. That simply means f of x over g of x all right, so there's my new composition of, my new quotient function. Now it says find the domain of this guy. Now notice, not only do I have a radical with the even index, I got myself a fraction. So I'm going to have to consider both of these questions. Will any value of x result in a 0 denominator? Yeah, I think something will. I'm not sure what it is, but I think something will. So my first strategy to figure out what will is to set the denominator equal to 0 and solve. You see how beneficial this little sheet is? So set my denominator equal to 0 and solve this guy. All right, I think I will add 1 to both sides. X squared equals 1. Take the square root of both sides. X is going to either be plus or minus 1. I'm going to consider both the positive and the negative square roots because either one of these numbers squared gives me 1. 1 squared, 1. Minus 1 is 0. Negative 1 squared, 1. Minus 1 is 0. Both of these numbers are problematic. So in my domain, x cannot equal 1 or negative 1. I got to keep that in mind before I write my final domain. All right, I've got a second thing to consider, a second question to ask. Will any value of x result in a negative number under a radical with the even index? Yeah, I got the same thing here. So I got this same thing here. So x cannot be anything to the left of 4. So what can x be? It can be anything greater than or equal to 4. Those are all good numbers. These are all good numbers. Now watch this. It can't be 1 or negative 1. Well, it's already not 1 or negative 1. So I don't have to worry about either one of these guys. They're already in the not acceptable value class. So 1 and negative 1 are not good values, but they're already in the not good value section. So my domain, it turns out, is exactly the same as my domain here, from 4 to infinity. Again, this is not easy. I recognize this is not easy. So you will have problems like this on your Hawks. You will not see a problem like this on your test. All right. 2 more functions. Find the formula for f plus and f over of these 2 functions and find the domain. Same as number 7, except my functions are different. So f plus g of x simply means f of x plus g of x. That means x squared, I'm going to put it in standard form, plus 4x minus 4. So there's my new sum function. Now let's find the domain. Let's ask the questions. They're at the bottom of your page. Will any value of x result in a 0 denominator? Nope, no denominator. Why not? No fraction. So, answer to question number 1, nope, no 0 in a denominator. Second question, will any value of x result in a negative under a radical with an even index? No, don't have a radical. So if I get 2 no answers, your domain is all real numbers. So my domain, all real numbers. And the way you mark that, all real numbers, in an interval fashion is from negative infinity to infinity. That's my domain. And for the record, anytime you have a polynomial expression like this, all real numbers is your domain. All right, let's find the formula for f over g of x. So f over g of x is just going to be f of x over g of x. So there's my quotient function. Find its domain. Anytime you're asked to find the domain, go to your 2 questions. Question number 1, will any value of x result in a 0 denominator? Hey, I got a denominator, and I'm suspicious that something's going to make the denominator 0. I'm not quite sure what it is, so I'll follow my strategy number 1. Set the denominator equal to 0 and solve. Set the denominator equal to 0 and solve. Divide both sides by 4. This is easy. X is 0. Now don't forget what you conclude in strategy number 1. When you solve the equation, you've just discovered what x cannot be. That's the one thing that x cannot be, is 0. So your domain is everything except 0. So far, my domain is everything except 0. But I need to ask the second question too. Will any value of x result in a negative number under a radical? There's no radical. So I don't have to worry about the second limitation. It's just the first one I have to worry about. So this is my domain, everything except 0. How do I write everything except 0? Remember this? It's from negative infinity all the way to 0. Don't include it because we're not including 0. Together with 0 to infinity. But don't include 0. It's the one thing that's excluded. This is how you say everything except 0. That's what you submit for your Hawk's solution. Hey, good luck to you on the rest of, or your specific applications of these problems.